Okay, so today's lecture is going to be on entropy. So entropy is just classified as S. So big S is M times little s. Delta S is just M times delta S. And we find the little s on the tables. And again, it's very similar to specific volume. It's specific entropy. And it's just another property. And there's some equations I'm going to talk about here in a second. But basically, we find these on the tables. Same thing if you're on the dome. Saturated vapor, it's Sg. If you're a saturated liquid, it's Sf. If you're in between, you got to use the equality equations. So where do we use entropy and what is it? Well, I'm going to show you here. Okay, so here's a quick bell ringer. Which one is better, or which one do you prefer? Assume that there are the same number of books. You have one that's stacked way high, and you have one that's really organized. Okay, so based on the first law, they're both equivalent. They have the same amount of energy, I want to say. This one might, don't worry about the potential. I'm talking about like the total number of books wise. The second law, though, high level of disorganization, entropy, from the stack of books. Okay, so this one has more entropy because it's more disorganized. That's kind of what entropy is. So what is entropy? Well, it's a thermodynamic quantity representing the unavailability of a system's thermal energy for conversion into mechanical work. Okay, so basically if there's irreversibilities, you're going to get an entropy increase, and thus less thermal energy for conversion into mechanical work. It's also a measure of disorder or randomness in the system. Okay, I'm going to skip that. All right, so the level of molecular disorder, entropy, of a substance increases as it melts or evaporates. All right, so just a quick idea. In the absence of friction, raising a weight by rotating shaft does not create any disorder, entropy. Everything is organized. The molecules of the shaft are all rotating in the same direction. Okay. The paddle wheel worked on a gas increases the level of disorder of the gas, and thus energy is degraded during the process. It changes the molecule's motion from being unorganized to highly unorganized. So more unorganized, more reversibilities, you're going to get entropy. So efficient people lead low entropy, highly organized lives. They have a place for everything, and it takes minimal energy for them to locate something. A library with good shelving and indexing system can be viewed as low entropy because of the high level of organization. Consider two buildings. All right, that's what we did on top of each other, all right, or the first slide. Okay, but based on the second law, the building would be the building of choice. Second building because it's more organized. Okay, so that's kind of a weird, entropy is kind of weird. Basically, it's just a measure of irreversibilities in the system. All right, so if we go back to this, we also use entropy to classify the second law, and we use an equation. So ds equals q over t. So q is actually the integral of t ds. All right, so this circle means that we're going to integrate from 1 to 2, 2 to 3, 3 to 4. So if we integrate the TS curve, you'll get the total net work, or total net heat. Sorry, not work. Work is the integral of PdV. Okay. We also can look at the increase of entropy principle. All right, so we have a coffee cup here. It can release heat to the surroundings. So if we look at the system, the coffee cup in the surroundings, then the entropy difference has to be greater than or equal to 0. Okay. All right, and I'm going to show you this in an example here in a second. So what we do is we call net delta energy or entropy that's generated. So generation. So if it's equal to 0, we have a reversible process, meaning that there's no irreversibility. So if it's greater than, there's friction or some sort of irreversible present. If it's less than 0, it's impossible. It's not going to work. So let me explain. So let's take a hot coffee cup, and it's in a room. We're going to have two cases. Case A is that hot coffee is getting hotter from the room. Okay, that coffee is 323 K and the room is 293 K. So based on the first law, or the second law, the delta S of the coffee is Q over T, Q over 323. Okay, and it's getting hotter, so we have a plus sign. Delta S of the room is negative Q over 293 because some of that heat is going into the cup of coffee. So when we add these two together, we actually get a negative 0 because this term is higher. This cannot happen. This violates the second law and actually violates fundamentals of heat transfer. Okay, the hot coffee cannot get hotter. It's got to get cooler. All right, and again, this is based on the first law. So using the same temperatures, but now it's leaving the coffee, so this is negative, and coming in the room, that's positive. When we add them together, we get greater than 0. Okay, all right, so this is whatever number we end up getting, we get generation. So this generation, if it's greater than 0, then it's possible, it's irreversible. If it's equal to 0, it's reversible. All right, so based on the second law, which is kind of entropy, we can classify the direction of heat flow now. And you can find entropies, changes from a system in the tables. So let's look at an isentropic process. So delta S is 0. That means it's adiabatic and reversible, both of those cases. On the TS curve, it's a straight line down. Right? And we can use a molar diagram to help solve some of these problems. So let me show you. So we have a steam turbine expands steam at 50 bar and 640 degrees isentropically to 0.2 bars. Determine the work done by the turbine. Based on steady state conditions from last chapter, we knew that the turbine is H1 minus H2 at the power. And we can use the molar diagram. So let's try that. So H1 is 3,750. So we're at 50 bar and 640 degrees C. So let's open up this. Just gotta rotate it. Okay, so here is entropy and here is enthalpy. Okay, and we're at 420 degrees, so these horizontal lines represent temperature. So 600, 550, 500, 450, 400. And then these lines that go across are pressure. All right. And then these are percent moisture. We don't need to worry about that. But we're at 50 bar. 50 bars right here. Okay, and we're at 420, which is halfway. Okay, so 420 is about right here. We're at 50 bar, which is right here. So we're right here at this point, right here. Okay, so what's the enthalpy? 50 bar in, was it 460. 460, which is right about here. So between 33 and 34, is that what we had? 37, was it 50 bar and 640? Oh, 640. Oh, okay, that's why. So we're at 640, which is way up here, and 50 bar. So we're right here, where this black dot is, right there. So about 3750. Okay. Now, in order to find H2, all right, we know that it's isentropic, so delta S is 0. That means S1 is equal to S2. And we're at what pressure? 0.2. So the enthalpy, you're going to go straight down because it's the same enthalpy. Okay, so we're at 0.2 bar, which is right here. So I've already marked it here, this black dot right here, straight down. So we extract over, we're at about 2350 or so, 2390. Yep. Okay, so that's how you use the molar diagram. And I will post the molar diagram. And then we just find our turbine. So if it's steam, you can use the molar diagram. It's really nice. We also have TDS equations for perfect gas. So delta S for perfect gas. We also have incompressible, materials. I think that should have been fluids. Okay. All right, so here's a quick example of a nozzle. So air expands polytropically through a nozzle such the exponent N is 1.45. The exhaust pressure of the air is 102 kilopascals and the temperature is 90 degrees C. If the inlet pressure is 400 kilopascals gauge, determine the change in specific entropy of the air as it passes through the nozzle. So here's our givens. It's polytropic. We're going to find delta S. It's steady state, open system, nozzle, and polytropic. Here's our delta S equations that I showed you previously. We found the R and CP off the table. We can find T2 over T1 from the polytropic equations I gave you a while back. Plug them back in, we get delta S is negative 0.042. Alrighty.